All right. What's up, Aaron? Everybody have a good weekend? Yeah? You had a good weekend? Yeah. Real good weekend. All right. So we're behind a little bit. We need to finish up 11.8 so we can move into chapter 12. We're supposed to, I believe, be. Remember we lost that one day, that holiday thing? Okay. Yes, we're supposed to be starting 12.3. We're not there. So we're going to try and finish up 11.8, which was Lagrange multipliers. So I sent the mini exam out. I sent it email, I believe. So check your Canvas email. It's due a week from today, right? It's like 4 problems? 5? 5 problems? Yeah, that's right. It's 5. Number 5 has parts A, B, and C, which you need to do one of them, but you can do all of them for bonus. Or 2 of them for bonus. It's up to you. All right. All right, so that test has some word problems in it. So this one is somewhat of a word problem. Find the point or points on this sphere, x squared plus y squared plus z squared equals 4, closest and farthest from a point given 3, 1, negative 1. So let's try and get our heads around visually what's going on here. We have a sphere. It's centered where? At the origin, and it has a radius of 2, all right? And then I have this point that's sitting out. Let's make this x and this y, this z. So x coordinate is 3, y coordinate is 1, and the z coordinate is negative 1. It puts us about right here. Okay, out 3 on the x-axis, out 1 on the y-axis, down 1 on z. And then we've got this sphere sitting there, right? So our sphere has a radius of 2, roughly, very roughly sketched out here. You know, it's something like, it's terrible. That's terrible. But we've got a sphere in here, okay? There it is. We're trying to find the point or points, in this case it's going to be points, on the sphere which are closest and farthest from this point. Make sense? Like visually what we're trying to find? All right, so how can we do this? This might seem a little bit overwhelming, but Lagrange multipliers tells us that if we have a function of 2 variables or 3 variables or 4 variables, it doesn't really matter, and we have a given constraint, that we can find the max and mins of that function, right? That's what it says. So let's just talk about what we're trying to find the maximum and minimum of. So when it says we're looking for the point or the points on the sphere that are farthest and closest and farthest from that point, we are trying to find the maximum and minimum what? Distance, right? A distance. A distance from this point, which is given, to some point on the sphere, right? Now, how can we use this whole idea, the Lagrange multipliers idea, to set this thing up? Any ideas? You're trying to find the maximum or minimum. You said distance, right? Okay. So what can we do?
The distance formula?
Let's use a distance formula, all right? The distance between 2 points. So hopefully this looks familiar to you. The distance between 2 points, x1 minus x2 squared plus y1 minus y2 squared. This is the distance between 2 points in 2-dimensional space. Does that look familiar? Comes from a right triangle and using the hypotenuse. And you can switch these. It could be x2 minus x1, y2 minus y1. It doesn't matter because you're going to square them. So what's the distance formula in 3-dimensional space? You just have to add one more thing out here, plus z1 minus z2 squared. So that is the distance that we, between two given points, right? That's our formula. Now, what points are we interested in here? Well, one of the points is given, right? So we could call this point right here, why don't we call this x2, y2, z2. And then the other point is what? Well, tell me about, I'm trying to find the distance between 2 points, right? One of them is this one for sure. But what about the other point? Is it actually fixed? I mean, any point on the sphere, right? Right? Any point on the sphere? No. Do y'all understand? We're just trying to figure out what x1, y1, z1 is, what x2, y2, z2 is. If I have 2 points, then this formula will give me the distance between those two. That formula, we want to find the max and min of, right? The max and min of this function. So I've been told, look, the other point or points are going to have to live on this sphere, right? But in general, if I just pick some point on this sphere, right? Let's just say that's definitely not the closest, right? But if I pick that point, I can tell you right now that that point has some x value, some y value, and some z value, right? An x coordinate, a y coordinate, and a z coordinate. But that doesn't make that point live on the sphere. What makes the point live on the sphere? That could be any point, right? What makes it live on the sphere? It would have to do what? Satisfy this right here, wouldn't it? So this right here is our constraint. That's our constraint. So what we're saying is this. Look, I'm trying to find the distance between this point and some arbitrary point out there, x, y, z. However, the x, y, z is constrained to that constrained by that equation.
So Lagrange multiplier is applied to the distance one?
We're going to do we're going to apply Lagrange multiplier method to this formula using that equation as our constraint. But our formula is not ready yet, okay? Our formula is not quite set yet. I needed to replace these things. So for us here, the distance will be the square root of, I'm going to replace x1 with just an arbitrary x, all right? Minus x2. For x2, I'm going to use the point 3. So minus 3 squared plus, for y1, I'm going to say y, and then minus 1 quantity squared plus z what? Plus 1 quantity squared. Now, do you all agree that the distance between an arbitrary point in three-dimensional space and this point is given by this formula? Yes? If I constrain the point x, y, z to that equation, then that point not only lives out there, but it's on the sphere. Yeah? So this, we could right now look at this. Now don't write this down. I could look at this as d is some function of x, y, and z, right? The distance is a function of x, y, z. So this is like f of x, y, z is this. And then I've got my constraint function, my constraint equation. The problem with this is that if we were asked to take derivatives now, because that's what we have to do, the derivatives of this is going to be kind of ugly because of the root, right? So we're going to use something that you probably used in Cal 1, and that's if you're ever trying to find the maximum or minimum of a root function, square root function, you can also just look at the square of the function. So we can make our lives easier by just squaring this and looking at that as our function. Now, that to me always troubled me as a student. Like, why am I allowed to just square it? I was told I can't just square something. Here's what's going on. I want to know when this will be the biggest it could possibly be, right? And the smallest it could possibly be. But everything in here, everything in there is positive, right? Positive, 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 no matter what. So if I can make this chunk right here in red, if I can make that as big as possible, then the square root will be as big as possible. And if I can make this as small as possible, then taking the square root will still be the smallest I could get. Does that make sense? The biggest this red thing can be is the biggest the root of it can be. The smallest the red thing can be is the smallest the root of it can be. Now, if some of these things were negative in here, this would not necessarily work out the same way. We would have a little bit of an issue. We would have to pay attention. So what I'm going to do to make our lives easier is we're not going to look at little d. I'm going to change the name of it. We're going to look at capital D. Capital D is a function of x, y, and z, and it is just x minus 3 squared plus y minus 1 squared, and then plus z plus 1 squared. And that is our, do you remember what we called that? The function we're trying to find the max and min of? I had a name for it. Objective function. This is our objective function, all right? So this is the objective function. All right. And then the constraint. This is what forces, the constraint is what forces that point x, y, z onto our sphere. So the constraint is x squared plus y squared plus z squared equals 4. And this side of it, right, this side right here is our g of x, y, z. So how many equations am I going to now set up? If I have a function of 3 variables, I'm going to wind up with how many equations? 4. The first equation that I set up is going to be the partial of f, or I shouldn't say f here, right? Because it's actually capital D. So I'm going to say partial of d with respect to x equals lambda partial of g with respect to x. Right? So you're taking the partial of this with respect to x, setting it equal to lambda times the partial of this left side with respect to x. So what is that? What's that equation here? What's derivative of this with respect to x? 2 times the quantity x minus 3, right? That's it? Okay. Equals lambda times 2x. Okay, that's my first equation. And now I'm going to continue. I'm going to do now partials with respect to y, then partials with respect to z, so on and so forth. So equation 2, 2y minus 1 equals lambda times 2y. Everyone good with that? Third equation, 2z plus 1 equals lambda times 2z. And what's the fourth equation? The constraint is your fourth equation. So just don't forget, this is your fourth one right here. So I'll erase it, but put it here. Equation 4, x squared plus y squared plus z squared is 4. All right. And now we have the pleasure of going through and trying to find x, y, z, and lambda that make all these true. Understand? I don't think I'm going to do that. I think I'm going to leave that to you. The part that I wanted to do was the setup of it, so you can see, okay? Is that fair? Okay. Now, keep in mind now that when you get your answer, you're going to be trying to find the x, y, and z that give you, that's closest and furthest, right? What if this question was asking, what is the distance between this point and the point furthest away on the sphere? Or what is the distance between this point and the point closest on the sphere? What would you have to do? Plug it in, right? Plug in the answers you get from this, right? Plug it into what, though? Yeah, not capital D, little d. You'd have to go take that square root and do it again, because that's the actual distance, right? All right, so let's see. Here's the visual of the problem. So there's 2 points here. You can see the blue point is closest and the red point is furthest away. Does that make sense?
Yeah, so the max is the farthest and then...
Yep, max is farthest. So when you, remember what you do once you find these, right? When you find your x, y's, and z's, you might have multiple x, y, z's. Multiple, right? Because all these different cases you look at. Once you get these, you take them, you plug them back into capital D. The biggest one is it would correspond to the point that's furthest, and the closest one would correspond to the point that's closest. Yes? All right. All right. I would work through that problem. We just don't have enough time. All right, now this is something we did not do last class. Can we kill one of these lights? Eric, do you mind? The one, I think it's on the far right. Yeah, is that okay, or are y'all going to go sleepy on me? You all right? Okay. I don't know. For some reason, it looks really washed out to me today when I look up here. All right, now, it turns out that you can use Lagrange multipliers when you have 3 variables and 2 constraints. You can have 2 things that confine the values of x, y, and z. So here's an example. Let's say that I had that same problem where I had that point, and remember we just had that sphere, right? Then the points that I could have found, right? The points that I found were on the sphere and it was closest and furthest, right? I could add one more condition to this. I could say instead of the other point living on this sphere, I could come here and maybe take a cylinder and just pop through that sphere with a cylinder. And if I do that, I would get, where it hits the sphere up here, I'd get this curve up here, wouldn't I? That's where it hits up there. And then where it hits down here, you would have this curve down here. Understand? Now, I'm asking what are the points that are closest and furthest from this point on the intersection of this cylinder and that sphere. So now the x, y, z's that live out here can't just be on the sphere. They have to simultaneously be on the cylinder. But the sphere has an equation, right? And the cylinder has an equation. Those are 2 constraints. Understand? And so we could set this problem up exactly the same way, but now we have 2 constraints instead of a single one. Y'all see kind of what I'm talking about? Now, how does it change the method? Well, it does create quite a bit of an issue, but there's still a process. So what you do to find the maximum and minimum values of some function of 3 variables given 2 constraints, so we have a g equation and we have an h equation. Those are our 2 constraints. You do the partials just like you did before, the gradients equal to each other, but instead of saying the gradient equals lambda times the gradient of g, you have to introduce another constant, adding to this, another constant times the gradient of h. So that's going to create, I'm going to move to the next slide here. You're still going to have 4 equations, still 4 equations, but notice the difference on your first equation. What's this Greek letter? Mu. Okay, so you have, first equation is partial of f with respect to x equals lambda, partial of g with respect to x. That's the same thing it was before. But now you have plus mu times partial of h with respect to x. So you're going to have x, y, z, lambda, and mu. You have 5 variables, right? 5 variables. We need 5 equations. The first 3 are still there, right? Those are the same. But now 2 constraints, right, gives us, it's not on here. There we go. 2 constraints, your first constraint equation and your second constraint equation give you your 4th and 5th equations. So there's just more variables in there, all right? Why do I, oops, this is wrong. Therefore, we are trying to solve a system. This should say what here? 5 equations.
So could we use matrices with this?
Pardon?
Could we use matrices with this? Or-
Matrices? What, can we do matrices on these? Why not?
Because it's not linear.
They're nonlinear. Now, could you get lucky and have a linear? You could, but I mean, man, that would be, yeah. I can't even see that happening. I just don't. All right, so there's the setup. Let's see if we have an example here. No, we don't. But I will give you a hint. You have a take-home exam, right? And I believe one of those has something about finding the distance between something in the intersection of 2 things.
Yeah.
I mean, this is what I'm talking about. Now, we haven't worked through a mu problem here. I'm just wondering if I need to. What do you think? Do you think you need to see one with a mu or not? You want to see one with a mu? Okay. I'll just pull one out of the book. I'm going to try and pull one that's relatively simple to work with. I put that homework assignment up last time, didn't I? Okay. There we go. Okay. Let's do this one. You have a function f of x, y, z equals 3x minus y minus 3z. And then you have two constraints. You have x plus y minus z equals 0. And then you have another one, x squared plus 2z squared equals 1. Can anybody tell me what this first constraint is visually? It's a plane in three-dimensional space. How about that one?
Yeah, it would be a cylinder, right?
It's like cylindrical. I heard ellipse. It's kind of like an ellipse, but it's free in one direction. What direction does it go out on?
The Y.
The y-axis. So it's kind of like an ellipse that's been stretched out, or not stretched out. It's like a cylinder, a circle, right? But it's kind of smashed a little bit in one direction. So you've got that, and then you've got this plane hitting it somewhere. And where the two of them hit together, you've got some like tilted ellipse. And those are the points that are valid. And you're trying to figure out the maximum and minimum value of this function on that. So I don't know if this makes any sense what I'm saying here. But you got a plane that's cutting through this squashed down cylinder thing. And wherever it cuts through, you've got these points, right? Those are all points, aren't they? Everything in blue there. So imagine that you've got this four-dimensional function. Your input, this is your domain right here. The blue curve is your domain. You're only allowed to plug those points into this function. And the question is, what's the biggest that function can get and the smallest that function can get if you're restricting yourself to just those points? Now you can't see this function, remember. You can't visualize it. It's in four-dimensional space. All right, well, let's set it up. We have our objective function, right? This is the objective. And then this is constraint 1, and this is constraint 2. So we're going to need 5 equations. The first equation is partial of f with respect to x equals lambda partial of g with respect to x plus mu partial of h with respect to x. I'm gonna let this piece right here be our g, and this piece right here be our h. Are they both functions of x, y, z? Is g a function of x, y, and z? Yes. Is h a function of x, y, and z? Even though y is not there, you can still consider that a function of x, y, and z. So we're good. All right, let's do this. Partial of f with respect to x. 3 equals lambda, partial of g with respect to x. 1, so that's just lambda, plus mu, partial of h with respect to x. 2x. All right? The first equation. Second equation. partial of f with respect to y equals lambda partial g with respect to y plus mu partial h with respect to y. So partial of f with respect to y, -1, equals lambda times partial of g with respect to y, g with respect to y. 1, right? So I'm taking derivative of this with respect to y. And then plus mu times partial of h with respect to y, that's 0. Okay, so there's my second equation. Any questions? Third one. Partial of f with respect to z. What is that? -3. Okay, so -3 equals lambda partial of g with respect to z, -1. So I'm just silencing my phone real quick. If it lets me. Stop moving. What the hell? Okay. All right, what was it? -1. So -1 and then plus mu partial of h with respect to z for z. All right, there we go. Let's clean these equations up. We still have the constraint equations, right? Those are here. Equations 4 and 5. I'm just going to leave them right there. All right, let's try and clean this one up. This one is 3 equals lambda plus, I like my constants out front, 2 mu x. All right, the next one is -1 equals lambda. Ooh, that's very nice. This one is -3 equals negative lambda plus 4 mu z. And now we're in business, aren't we? I mean, this right here is kind of like the ultimate saving grace, isn't it? Because I can just replace all my lambdas with -1. So if I do that, let's rewrite this equation. I'm going to change colors to let you know I'm about to replace lambda with -1. So everything I do in blue here. If I replace this with -1 and then move it to the other side, that becomes a 4, right? And then I can divide both sides by 2. I get 2 equals mu x. That's after I plug lambda's -1 into that one. When I plug lambda's -1 into this one, it becomes a +1. And then I subtract 1 from both sides, I get -4. And then I divide by 4, and I get -1 is mu z. Agree? Now what? When I plug -1 into this, right, which gave me a +1, and then I subtracted 1 from both sides, which made that a -4, right?
Oh, yeah.
Yes? Sure? And then divide by 4. So at this point, what would you do? You could solve each of these for mu, right? You could, and set them equal to each other, or what do you want me to do? Doesn't matter to me. You want to solve this for mu real quick? If I solve that for mu is equal to what? 2 over x. Okay, but you just created a potential problem, didn't you? So you'd have to say that x couldn't be 0. I don't like that, though. Okay. Here's what I'm going to do. I mean, you can, look, at this point, you can solve that however you want. And you'd have to look at some certain restrictions. But here's something that I'm going to do that you might appreciate this as being nice. I don't know. Okay, so look, this is what we've got here, and then this one right here, right? What would happen if I multiply both sides of this by -2? Why would I do that? What's the left side times -2? +2 equals what? -2 mu. sorry, mu z, right? Okay, so I can turn that into that. Now, if 2 equals this and 2 equals that, then I can set them equal to each other, can't I?
Yeah.
Okay, so this would mean that ux, mu x, it's Monday, equals what? Negative 2 mu z. All right, now what?
You can solve for x.
How? Divide. I don't want to divide. I don't want to do anything like that.
You said it's equal to 0.
Are you gonna
Move everything to one side. Okay, right? What I'm trying to do is avoid dividing through by things that I can't control. Factor the mu out, right? Factor it. And then x plus 2z equals 0. And now set them each equal to 0. So I'm going to be looking at two different scenarios here. What if mu is 0? And the other one, x plus 2z is 0, which means that x would have to be equal to negative 2z. Now what?
Well, mu can't be 0
Why can't mu be 0?
because with with equation 1, if mu is 0, that means 3 would be equal to negative 1, and that can't happen.
Okay, so we can eliminate mu being 0. Was it the third equation? Which
The
equations?
first one, the first or the third one. Either
The
one.
first or third? I thought the first had lambda in it, though.
Well,
Please
submit.
we solved for it to be 2 equals mu x.
Oh, is 2 equals mu x?
Yeah.
Oh, that was after lambda was forced to be negative 1. Okay, I'm sorry. I was thinking before we forced lambda. Okay, so yeah. So is everyone okay with the idea that this right here can't hold because of one of the equations wouldn't be true? So that's not considered. We're not going to consider that. Now, the other scenario is that x equals to negative 2z. How does that help me? Which one?
Equation 5.
Should I go constraint 1 or 2? 2? Why not 1? Why shouldn't I just plug this one into constraint 1? Because it's linear, it's easier to work with. That has a y in it. This has just x and z. So if I plug in an equation that just has x and z in it, then I'll be able to solve for one of those variables. So I'm going to take this, and that's about to get plugged into constraint 2. All right? That's what's about to happen. So when I do that, I'm going to replace x with negative 2z. So this constraint equation becomes negative 2z squared plus 2z squared equals 1, which gives me 4z squared plus 2z squared equals 1, which is 6z squared equals 1, which means z squared is a sixth, which means z is equal to plus or minus root 1/6.
Remove a little dash from the 2 on the first one because it's negative z times z squared.
Pardon?
So if you look at the top, you had accidentally put a strike through the 2, unless.
Did I? Oh, I struck them both. That's a sleepy 2. He wants to be a Z. He wants to go to bed. Thank you. Good? Okay. So once I know what Z is, I can go get X, right? Now X is negative 2 times Z. So let's start writing some solutions down here, all right? And man, where should I put them? I guess I'll put them right here. When I talk about solutions, what I mean is I'm going to have an x, y, z, lambda, mu. It's actually an ordered, not an ordered triple, not an ordered quadruple. Quintal? Yeah, it's an ordered, yeah, it's not even, because what would happen if it was like 17 things, right? You would just kind of run out of obvious names for it. So we've got this includes all 5 variables. Now we know that The z can be one of these, right? What about the lambda? It was -1, wasn't it? That was -1 all the time. But I could have, I'm going to write this as 1 over root 6. And then another answer I have is -1 over root 6. -1. I still don't know what mu is. And actually, I don't really care to find mu. I mean, like, I don't have to find mu. The most important thing is x, y, z. But it doesn't hurt to go back and get them all. All right, so those are my two possibilities. Now, what about x? Is -2 times the z, right? So this is going to be -2 over root 6. This one will be +2 over root 6. Understand? Multiplying both of those by -2. Well, let's just get our y now. Let's get our y. How are we going to get our y? What equation are we going to use? We're going to use the first equation. So let's go to equation, constraint 1, sorry. Constraint 1 tells us that x plus y minus z equals 0. Another way you could write that is y is equal to z minus x. Right, just solve that for y. Because that's all we don't have, right, is the y. So y is the z coordinate minus the x coordinate. What would that be here if I took the z coordinate and I subtract the x coordinate? It'd really be adding it, right? So 3 over root 6. And if I took this and subtracted this, I'd get -3 over root 6. It appears that I only have 2 critical points, right? 2 critical points. So I'm going to take these, and what am I going to do with them? Plug them into the objective function. And then the biggest is going to be your max, and your smallest is going to be your min. Okay, does that make sense? That's how you'd work with it. Now, the mu was pretty nice. I mean, like, the mu didn't really have a super big impact because that lambda was -1, right? And they do keep these problems relatively on the nice end. And they make it so you can solve these systems. Because once, I mean, in general, solving a nonlinear system of 5 unknowns and 5 variables, 5 unknowns and 5 equations in general is a very difficult thing to do. Nonlinear. There's not like, oh, we just always use this method and it always works. I mean, that's a very difficult thing. That's where computers are really effective. All right, that's it. We're done with that section. Is that all right with you? We'll move on.
What happens if we're not all right with it?
Pardon?
What happens if we're not all right with it?
If you're not what?
All right with it.
At least I know you're not okay with it. I'll put a little mental note. They were not okay with that, and we proceeded. I'm sorry? I'll get that going. Hold on. All right, can you all see the homework up there? Okay. Should be right here. Yeah, I took attendance last week, didn't I? Yes, I did. Yes, I did. Very proud of myself. I think I remembered too. No one reminded me.
No, I think someone did.
Did someone remind me? Yeah, probably. Here, you get it first. All right, here we go. We are moving on to a new chapter in the book. 2 more chapters to go. We're like halfway through the material. And now it gets difficult. No, I'm kidding. All right, so chapter 12 is called Multiple Integrals. Multiple Integrals. I don't have that title in my notes. I just have the title for 12.1. So the title of the chapter is Multiple Integrals. What we're going to do is start out with double integrals, then we're going to go to triple integrals, and then we're going to go to different coordinate systems. We're going to look at, well, I should say, double integrals in a different coordinate system, then triple integrals, and then triple integrals in 2 different coordinate systems, both spherical and cylindrical. And then we move from, then we do some applications, and then that's it for multiple integrals. Like, we are not going to do like quadruple integrals or anything like that. And it's, again, just a restriction on the the visualization of it, we start to lose sight of it. But there are such things as quadruple integrals, and you can keep going. So, and then we'll get into chapter 13, which is the vector calculus portion of the course, where we start bringing vector fields in and start doing different types of things called like line integrals and surface integrals. And we will end with Green's theorem, Stokes' theorem, and the divergence theorem. So that's our path. But we got to start here, double integrals. So we're going to spend a little time talking about Cal 2. So, this says in Cal 1. In Cal 1, Cal 2 / depending on your instructor, hopefully you saw Riemann sums. How many of you saw Riemann sums? Okay, who did not see Riemann sums? It's okay if you didn't. I just need to see. Maybe you've seen them, but you don't recognize the name. All right. So the way it works in Cal 1 when we're trying, or Cal 2 when we're trying to figure out the area underneath a curve, is we take a function like this blue function right here. We say, hey, what's the area below that? So we take rectangles and we try and approximate that area. And we would say, okay, if you take the area here, and add them all up, you would get approximately the area underneath that curve, right? And how do we make it a better estimate? How do we get a better estimate? We could do triangles, or we could do more rectangles, right? And if you have more and more rectangles, then what you're doing is you're reducing all those little gaps. You're creating less and less error, E-R-R-O-R, less error. And if you could possibly somehow let the number of rectangles go to infinity, then the answer would converge towards the true actual area. And when you take all these rectangles and you try and come up with a formula that gives you the sum of those, it's called a Riemann sum. It's the formula that you use to actually calculate by hand that sum. And it's usually a very ugly formula. So that's what I say here in red. If we let the number of rectangles go to infinity, we get the true areas. So this notation, this is the sigma notation. The sigma notation, this means take the sum f of x sub I times delta x, and you're summing from I equals 1 to infinity, basically. This notation meant for each of those rectangles, I'm going to back this up. Okay, go with wider rectangles so it's easier to see. If we were to say that this right here is the measurement is delta x, they're all the same. All these rectangles have the same width, right? Delta x, delta x, delta x. And then the height, let's just take one of these. I'll just pick a special one. I'll do it in blue. This is like delta x, but if I pick a point here, this right endpoint, I call that, let's say, x sub 3. So this would be the first x sub 1. This would be x sub 2, x sub 3. If I pick that right endpoint, I need to switch something on my picture, sorry. If I pick that right endpoint, x sub 3, and I take this right here and measure this height right here, right there. How tall is that? How high is that rectangle? It's f of x sub 3. It's the height of the function at that point, x sub 3. So what's the area of this rectangle right here? What's its area?
Delta x times delta y.
It's width times the height, right? So it'd be f of x sub 3 times delta x. Okay? That's the formula that gives you the area of just that single rectangle. What this formula in red is saying is, you know what? This is not infinite. This is n, and we're taking a limit as n goes to infinity. Okay. But what this formula is saying is this. if I were to start at the first, at 1, that would give me this point right here, and I were to do f of x sub 1 times delta x, it would give me the area of that first rectangle. Then I move to 2, that's what the summation does, right? It keeps changing, goes 1, then 2, then 3, then 4. So then that would give you the second rectangle, and then the third, and then the fourth, and the fifth, right? That's what that basically is saying. If we take the limit of this formula as the number of rectangles go to infinity, we get the true area. That should have been made clear in Cal 2. That's what's happening. The reason why I stress it, one of my former students is going to make me really happy right now, and they're going to tell everyone why I stress this so much. No? Not going to happen. Okay, so let me ask, isn't there an easier way to find the area under a curve not using these sums? What do? You do integration, right? And so if I were to like label this right endpoint here B and this left endpoint here A, and then tell you that this is the function f, what would be the notation that I would use right now to represent the area under that curve? Integral a to b f of x dx.
No.
This is, what do you mean the same thing?
I mean, don't we get this from the series?
No, yes, okay, so this formula, the answer to it is this, right? Like they're the same answer. The reason I like to write this formula on the board and then later on show the students this is because you can see the formulas like where it came from, like what each part is. This delta x turns into your dx. Why does it turn in from delta x to dx? Because you're letting the width of the rectangle, delta x, you're letting it become infinitesimally small. It's a little tiny little infinitesimal width. So that delta x becomes the dx. This f of x sub I just turns into the function. So you're evaluating the function at points within your little rectangles. And then this integral symbol is just a fancy way of saying take the limit as n goes to infinity of from the summation as I goes from 1 to n, right? That's all that is. So you can see the parts of the formula here from the Riemann sum. All right? Now that's important because when we set up a double integral now, we can sort of generate this formula again from the picture. Maybe, we'll see. I mean, we are, but it'll depend on you whether or not you follow that. All right, so that's what we did in Cal 1 or 2. You saw Riemann sums and some of you didn't. I don't have my students calculate Riemann sums by hand because they're tedious. All right, so we're going to take this. What's wrong? You don't like this? What?
It looks like
You're laughing at this?
Did you draw a solder joke?
Really? Is it that bad? Wow. I wasn't expecting that reaction. All right, this is a different visual representation that apparently is hilarious. This is a different representation of the same exact concept, okay? So what I want you to see here is if we're trying to find the area underneath a curve, we can look at a sample slice of that, okay? A sample slice. The sample slice has a width of dx. Now, when I put dx here, I'm using the infinitesimal. I'm using the idea that the limit, I'm going to have an infinite number of these in here. So, or I'm letting it become infinite. So that's going to be an infinitesimal slice. And the height of it is just the function's value at any point inside here. That's what that x sub I means. But I've also included some other things here that become very important as we proceed. Notice you can see the entire domain, like I'm integrating from a to b. So if I look at that a to b here, here it is just by itself, the domain isolated alone. Here's the domain with the function, okay? The area, again, on AB is this limit, that summation thing again, which became the integral. Yes? Okay, nothing new there, just a different kind of visual that y'all apparently love. We now try and look at trying to find the volume under a surface using Riemann sums. So let's say we have a surface, right? Three-dimensional surface, and we want to know the volume underneath that. How could we figure that out? Would we want to add up the area of rectangles? Would that work?
We could do basically the domain and then the x, y, z, or the, let's say x, y, and we get a sliver, and we can make that infinitesimally small and get the area of each sliver.
Okay, so let me try and do this. We have a surface sitting here, right? Three-dimensional surface sitting above the xy plane. And you're saying we should look at the domain, which is on the ground. So remember we were trying to find the area between A and B a second ago? Well, if I'm trying to find the volume under a surface, I need to actually give some restriction to the domain. Yes? Okay, so I could restrict, let's say, this from A to B. And on the ground, that would be all the stuff in there, right, and below this thing. Where else could I restrict it? On the y-axis, maybe between, not A and B, I already used A and B. C and D, right? Let's use C and D. C and D on my y-axis, and those would run this way like this. And now what I'm talking about is just taking points that live in here and taking anything that lives, I don't want to do that. Taking points in here, and then just imagine taking everything and mapping it up in here into this surface, you know, wherever they hit, and it would create something up here like this, and then all the volume below that. Understand that? Now back in the two-dimensional picture, when you go from A to B, we cut these into rectangles, right? Cut those rectangles. And now, but here you can't do it because we're trying to find the volume under this, right? Areas give you areas. How are we going to get volumes? We just box them up. How about we do like boxes? Okay, so let me grid out. You know how we just cut up, like we did delta x, or like, yeah, we did, right? Delta x, the widths were all the same. If we were to do that same concept here, we could grid out in this direction, right? We could grid out with an infinite number of partitions like that. And then we could grid out the C to D the same way. And what we would have is a bunch of different little boxes, or sorry, rectangles or squares on the ground, right? And then I could take just one of these squares and just plug it in, get a little thing up here, whatever it looks like, and then try and find the volume of that piece, yes? And then add them all up. That's the concept. That's the concept. Now, we're going to go through the formula, like we're going to create the formula in a second here, but here's to convince you it works. So here's a surface that has already had this grid cut out on the domain, on the ground, and created a bunch of boxes. And what I have here is 5 boxes across, 5 boxes deep. And so we're going to have 25 boxes, and if you add up their volumes, you get an approximate volume. And this computer is saying that the approximate volume of this is 40.96. The true volume underneath this surface, which corresponds to that picture right there, the true volume is 42.6667, keeps repeating, but so how could I get a better approximation? More boxes, right? So I could do a finer cut. I could cut more this way, right? And then if I let the number of them go to infinity, which I can't, my computer won't do that, but I can go 40 each way, it starts to get pretty darn good, you know? It starts to look pretty smooth. You have less error in there. So same exact concept as the two-dimensional case, right? Now let's set it up. Let's see how we get the formula. I'm going to have another pretty picture for you here. What's wrong with this? Yeah, do y'all not like the colors? What?
Just the bright colors.
The quality sucks. It's okay. I used to do a tablet that I wrote on. That I would write on a tablet, and I would record the screen and my voice, and that's what I would put up on YouTube instead. So I still have these recordings. What was cool about that is with the tablet, I could use different colors real easily, and yeah, whatever. Why didn't I stopped using it because I was like standing looking at a tablet the whole time, and I prefer to like stand up here and move my arms, and it was just, I don't know. Yeah. So you know how like dull and boring I am to begin with? Like imagine me just standing here, like it'd be even worse. All right, so this picture is really like the same thing we had a second ago, but now we're talking about this surface in three-dimensional space. So we're looking at the domain over here, which is really the piece that's on the ground here, and then the surface is above this, and we're taking one sample rectangle. Now we really call that a parallel pipette. I'm going to call it a rectangle or a rectangular box or a box or something, but it's a parallel pipette. It's a rectangular box, it's a shoebox, okay? So if we go back to the domain, we were going to grid out, right, like this, and then cut it like this. So if we take an arbitrary slice here, that's delta x, this would be delta y, and then we pick some random point inside that box, and since it's a point in two-dimensional space, it's going to have an x-coordinate and a y-coordinate, right? I'm going to take that point, take that little box, which is this right here. I take that point, I plug it into the function, it's going to have a height, right? It's going to spit out a z value. I'll use that as the height of my little box here. So what is the volume of this single box? Length times width times height, right? Length times width times height. So the length and width are delta x, delta y. I put those here at the end. And then the height is the function's value at that arbitrary point that's in there. Turns out, and I didn't say this earlier, it turns out it does not matter where this point lives, as long as it's in the box. And you might be thinking to yourself, well, why? Because you're going to have a different value. Because the box is about to get infinitesimally small, so that point's going to start to converge down to 1 point. And so it won't matter. So the volume is approximately that, right? That's the volume. The volume below the surface, just over that little rectangular region, is approximately my rectangle, my rectangular box. So if I want to get the total volume underneath the surface over the entire blue highlighter color there, then what I'm going to do is I'm going to have to add up. Imagine we're going to add up just this row first. So we're going to take this box, this box, this box, and then move this box, this box, this box, and then move again this box, this box, this box. So we're going to start on one row, we're going to sum through, and then we're going to move and sum through again, and then move and then sum through again. And so what you wind up having is a double summation. So imagine this part right here, it's a double sum. Yes, the quality sucks here. The double sum here, ignore this one. This first one would just move you across that first row. And then you let the index go up one, that shifts you up to the next row, and then you sum through again. Then you move up to the next row, you sum through again. And then what you do is you take the limit as those go to infinity. And what you get is from each one of these summations, you get an integral sign. So you get a double integral. Then you have the function evaluated at x, y, that's here, and then you get delta x, delta y. Now I do have this written down in a better way. This is just a repeat. I do have it like typed up. There it is typed up, so that looks better. This is the final kind of conclusion here. The volume between some surface, f of x, y, and the xy plane, which is the ground, over the rectangle R equals AB cross CD. So this is only over rectangles. This formula does not work if your domain is not a rectangle. And we are headed there, okay? We are going to integrate over things other than rectangles. If it's a rectangle, it's a very straightforward setup.